Jupiter's moon Io is the most volcanically active world in the solar system. But why? After all, Io is only slightly larger than our own moon, shown here to scale with Io, and you know from earlier chapters that our moon is geologically inactive because of its small size, which has by now allowed its interior to cool. Because the whole solar system is about 4.5 billion years old, the fact that Io does not also have a cool interior must mean it has some ongoing heat source that our moon does not have. Scientists have identified this source as what we call tidal heating because it is caused by tidal forces that are particularly strong on Io for two reasons. First, while Io's distance from Jupiter is similar to our moon's distance from Earth, Jupiter's much larger mass, more than 300 times Earth's mass, means its gravity creates a much stronger tidal force on Io than Earth does on our moon. If you now recall that Earth's tidal force on the moon caused the moon's synchronous rotation, in which it always shows nearly the same face to Earth, you won't be surprised to learn that Io and other moons always keep nearly the same face to Jupiter. If Io had a circular orbit and therefore kept exactly the same face to Jupiter at all times, the tidal force across it would never change and there would be no tidal heating. So the second reason for tidal heating is that Io's orbit is slightly elliptical, which means the precise tidal force changes as Io orbits. This animation shows the idea. The red arrows represent the gravitational attraction of Io's near and far sides to Jupiter, so the tidal force is a difference in these attractions at any point. Notice that the tidal force is stronger, creating larger tidal bulges when Io is closer to Jupiter, and weaker, creating smaller tidal bulges when Io is farther. This continually changing tidal force and the wiggling of the bulges caused by Io's elliptical orbit flexes Io's interior and is the source of its tidal heating. Keep in mind that the tidal bulging is highly exaggerated here. In reality, it would not be noticeable to your eye. However, we are still left with another question. Most large Jovian moons have nearly circular orbits, so why is Io's elliptical? The answer stems from what we call an orbital resonance, in which Io orbits Jupiter exactly twice for each orbit of Europa, and exactly 4 times for each orbit of Ganymede. This animation shows the orbits. The counters in the lower right show the 4 to 2 to 1 ratio of the 3 orbital periods. Notice that the resonance creates periodic alignments that cause the moons to tug on each other gravitationally in the same way each time, and these tugs keep the orbits elliptical. Orbital resonances among nearby objects like these are very common, and arise for reasons very similar to those causing synchronous rotation. Now try this question to check your understanding. How does tidal heating on Europa compare to that on Io? Is it stronger, weaker, the same, or is there no tidal heating at all? The answer is B, weaker. Because Europa orbits farther from Jupiter, its gravitational attraction to Jupiter is weaker, which also makes the tidal force across it weaker. As you'll learn in your text in your class, this weaker tidal heating also explains why Europa is not covered by volcanoes like Io, but is still thought to be strong enough to melt part of Europa's icy crust into a subsurface ocean of liquid water, perhaps with volcanic vents at the ocean bottom. That is a major reason why Europa is considered to be one of the most promising places to search for life beyond Earth.